All right, let's talk for just a few minutes. Take a high level view. What exactly is a neural network? So, a neural network, as the name implies, is loosely modeled after a biological neuron. Here's a quote from one of the folks that pioneered the concept. So, a computing system made up of a number of simple, highly interconnected processing elements which process information via their response to external inputs. And neuroscientists will tell you that the brain works roughly, roughly like this. Now, the human brain is more complex than the networks we can build, obviously. But this was the inspiration for the idea of a neural network, which has been around for quite some time. These neurons, so this graphic right here, that's known as this graphic right here, this is known as an artificial neuron. Uh, and these have been around for some time. Um, Here, this graphic is a biological neuron. So you've got inputs, there's some processing, and the synapse, the information it's said to travel down this axon and jumps to the next neuron via these synapses. In a similar, certainly not identical fashion, but uh, in a similar fashion, neural networks can be connected together to form more complex networks. Um, Here we see we've got an input, we'll call this x1. We've got an input, we'll call it x2. We've got a bias, in this case the bias is 1, which most of the time it will be, more on that in a second. The strength of these inputs is controlled by the weight. Here's weight 1, so this weight W1 is the weight or the strength of input x1. Here weight W2 is the strength of input x2. They get summed here. The sum is often referred to as h. And then there's this f of h. This is an activation function. So it controls whether or not the neuron, or the neuron, in this case, we're going to call this an artificial neuron, whether or not it fires. So this is very simple, but this is the structure of a neuron or an artificial neuron. And again, neurons are combined to perform complex networks. Thousands or tens of thousands of these things can be combined. So let's continue. What are some of the elements of a neural network? So generally, and here, this is a slightly different view. It's meant to portray the same information, just a different view. We generally have, starting at the top, an input layer of neurons. So here, this red, this is the input layer. Now, note what's going on here. Each input goes, and well, let's start. We have an input layer, then we have an output layer. So this is the output over here. We may have hidden layers of neurons. So here's what's a so-called hidden layer. Now notice what's happening here. Each of these inputs has a weight, but each of these inputs is going to another neuron in this hidden layer. So here's an input, here's an input, here's an input, so it's going to here. Here's the first one again, boom, boom, boom. So each one is going to every other one. There's an activation function that fires for each layer. So there's an activation function for this layer. There's an activation function for this layer. So this is the basic structure and the basic elements. And finally, there's a loss function to reduce overtraining to reduce overtraining of the network. Here's how these work. This is a supervised learning technique. What that means is these inputs, these are labeled data. We know the result. We know what the data is. It's labeled. We have some output. We're going to compare the output with the output of the neural network with our known results. So the difference between truth and the output we got is known as the loss function. This loss function is used to train the network via a process called backpropagation. Based on this loss, we're going to backpropagate this error back to the input layer, and we're going to adjust the weights or the strength of each input. We're going to adjust the weights until we achieve the desired result. So this process can happen, thousands or tens of thousands or millions of times. So there's weights for each input that get adjusted based on this backpropagation. The network is subject to an activation function which causes the network to fire. So let's talk a little bit about weights and activation. So here, another simplified diagram. So here again, we have x1, w1, x2 times w2. We have our bias. We sum these. We get h. H equals the sum of the wi times the xi plus this bias, and then we apply this result h, some f of h, where f is this activation function. What does that mean? So you can view the activation function as a threshold. Does this sum of weights and inputs plus bias exceeds some threshold? Now, the activation function can be pretty much any function you want. The activation function can be pretty much any function you want. A common choice, a very popular choice, is this function called a sigmoid. A sigmoid is 1 divided by 1 plus e to the minus x. And here's what it looks like right here. You get this nice, smooth, differentiable, continuous curve. So let's look at that just a little bit more closely. We have this activation function here, 1 divided by 1 plus e to the minus x. We have this activation function, and here is this nice, smooth, continuously differentiable curve. And think of what we're trying to do. We're trying to threshold the output. Now, maybe it would make sense to just use a step function, right? If you meet some threshold, the output is, for example, if you meet some threshold, the output is true. If not, the output is false. For reasons we're going to talk about in just a second, we can't really use a step function because a step function is not continuous. A step function is not differentiable. But let's look at this sigmoid function. So here it is. Here's the same thing. 1 divided by 1 plus e to the minus x. And it looks, visually it looks slightly different, but this is just zoomed out. You can see it's really the same thing. Let's see what happens when we adjust this. So if we make it small, see it starts to get almost like a straight line. We'll go back to 5.5, got a shallow slope. Back to 1, minus 1. It's got the same slope we've been looking at. Let's see what happens if we make it 10. Okay, this slope is getting pretty steep. Let's make it 100. The slope is getting really steep. It's starting to look like a step function. Let's make it 1,000. You can see, and you can pretty easily see what happens. So this is why we use this sigmoid function. It's smooth, continuous, and differentiable. Why do we care if it's differentiable? We care if it's differentiable for use with this loss function. And loss function and gradient descent. So the loss function, pretty simply, remember what we're doing here. This is a supervised learning technique. So we're comparing the output with our known input samples, and the loss function just tells us what is the difference, because we're feeding this with known data, and we're looking to see, can this network recognize this known data. And we're looking that the error is the loss function, the difference in truth versus the network output. The idea is to adjust the weights in the neural network using this back propagation, using this error calculation. And these are trained using a known set of data. But we're going to take this error, we're going to propagate it back, and we're going to adjust these weights until the output meets or approaches the desired input, until the desired, but remember the input was truth, supervised learning. The way we do that, we use a technique called gradient descent. And if we take the gradient of the loss function, and we're going to eventually we're going to walk toward, or we're going to descend towards the minima of that loss function, and that's the place where the error is the least. So for that reason, we need a function that is continuous and differentiable. So you can see that that sigmoid function fits the bill perfectly. It's continuous and differentiable. It can approach or approximate a step function. Here it is again. So dependent, it can get pretty steep pretty quickly. And we use this back propagation. We propagate this error back to adjust these weights. So at a high level, this is how this works. This is how this works. In our next video, we'll look at a code example, but this is probably good for now. So thanks, and that's it for now.